Okay, let's take a second look at the IV curves of the NMOS and PMOS. So for NMOS, they have VDS versus IDS. VDS, which is a voltage from drain to source. If we ground it, this is VGS, and this is IDS. That's drain, source, gate. Okay, so VDS versus IDS looks like this. You'll run lab this week on Thursday, so we'll know. We'll look at the details. And VG1, VGS1, VGS2, VGS3, and definitely this is the largest. Okay, so VDS set is not a voltage on the line, it's a voltage on the x-axis. It's over here. It's called VDS set. And that equals VGS minus VTHN. What is VTH? The threshold voltage of the NMOS. .8 sometimes. So for the C5 technology, it's 0.8, I think. It's very close to 0.8. Okay, so that's VDS versus IDS. So for VGS versus IDS, it looks like this. And this line here is a VTHN, is a threshold voltage. You can draw these two curves, and without the labels, you can get 100% on the quizzes in the future. Okay. So this line here is a bigger VGS or lower VGS. Oh, VDS, I'm sorry. Which one has a bigger VDS? This one, right? This one has a large VDS1, VDS2, so this is the largest. Why? Because the same voltage, same VGS, this guy has a higher current. Right? Any questions on this? No? And there's the cutoff region here with the VGS lower than VTHN. So this region is called what? Cutoff. It's a cutoff region. Same for PMOS. Just change the labels. I'll do this really quick. I'll do this really quick. Don't have too much time on this. So PMOS relies on a voltage between S and D, S and G. So S and G's voltage drop is called VSG. And you can ground here, no problem. And you do need a VSD as well to drop a voltage across S and D to drive current from S to D. Okay. So remember it's VSG. So in a lot of other textbooks, they use VGS as well, but the threshold voltage becomes negative. We don't like that. So in our textbook, we just use VSG instead, so we can use a positive threshold voltage. So VTHP here is around 0.9 volts for the C5. So VSG has to be larger than 0.9 volts in order to turn on that channel. Okay, so VSG, not VGS anymore. In that case, the two curves look like this. We have VSD. Keep in mind, it's VSD. And ISD. We're looking at current from S to D, not D to S. Okay? So it looks like the same pattern as NMOS. And you can draw a curve here. And the voltage at the x-axis here is called VSD set, which is VSG minus VTHP equals this value, right? Definitely there's a cutoff region here as well. And this is VSG VSG1, VSG2, VSG3, and that's the largest. It definitely also has a VSG to V to ISD curve as well. All right, like this. So it looks like this. And here's VTHP, about 0.9 volts. So you may see different curves from the lab tutorial. It's because they flipped the direction of the current or the voltage. Let's take a look at it real quick. So when you are working on the lab this Thursday, you'll see curves slightly different from the one I drew on the paper. For some reason it's kind of slow. So for example, if it's that looks like, couldn't remember. Oh, like this. We drew things like this. MOSFETs and IV curves. Just take a look at the curve to see if that makes sense, like things like this. Okay. So this one plotted the PMOS, which is this guy. Okay. And VD, let me take a look. It's from 0 to negative voltage. The reason for that is, also first, if we just look at this curve, is that a VDS, no matter VS or VDS, is that VGS to IDS or VGS to VDS, IDS? Definitely the y-axis is the current, right? Y-axis is the current. So the x-axis is going to be VSD. But why plot it this way? Let's see how the spice code is written in here. So PMOS, no problem. We got SD, G here. And that's a tap. That's a body contact. So for PMOS, which body contact do you need over here? For PMOS. PMOS is an N-well, right? So you need an N-tap. Let me draw this for you on the paper real quick. So this guy is an N-well. That's a P sub. So in the N plus here. Okay, and the N plus cannot be outside of the N-well. Then it doesn't work for anything, right? It has to be inside the N-well. So it's in order to short to the N-well, and eventually you short this one to where? To VDD. To a highest potential of the circuit. Why? Because it forms a diode here. Okay, form a diode. You want to short the cathode of the diode because N well and N plus they are same material that are shorted. So you want to short the cathode of the diode to the highest potential of the circuit, so it's never getting forward biased. It's undesired parasitic diode. Now let's take a look at this. How the SPICE code is written here. So VS from S to 0 has a DC voltage which is 0. So when you are doing DC sweep, it's a dot DC. When you are doing DC sweep, you don't really need to assign a DC voltage here because you are going to sweep it through a certain range. That's just a certain rule of the SPICE. If you guys are not really familiar with SPICE like this, we can have some assignment later. But how many of you know how to do a DC sweep? DC sweep? Did you learn that in certain one? No? AC sweep? No? Okay. A little bit? Okay. So we probably have to do it a little bit. Super important, fundamental, right? W, which is over here. Why is called W? It's a well contact. That's why it's a while, right? It's a while contact. It's N-tap. Connect to N-well. G is the voltage of the gate. D is the voltage of the drain. And you can see it's all 0 volts. Okay. And VD is doing a dot DC. It's a DC sweep. It's from VD to 0, right? VD is this guy to 0. Oh no, sorry. It's a DC sweep for VD for this guy, voltage at this node. And it's sweeping from 0 to -5 volts. Okay, so let's draw it on the paper so make sure it makes sense here. Yeah, it's confused people a lot in the past. But what's really going on here? Here's a PMOS, okay? Source, drain, and gate. So if you do a cross-sectional view here, and you are going to see, I'm going to draw it on this side. Drain. Here's source, okay? Here's in N-well. And here's N plus.
You're a little bit off-centered.
Yeah, thanks. Here's source, for example, okay? Source. So right next to source, I have a N-well tap, which is this guy. I can see those little dots. All the little dots. So the dots is part of the mask to tell the foundry to deposit a N-well into the wafer. Okay? So in that case, if you have an overlap between these dotted area, let me zoom in one more time, just further. What's the dots? You can. You can see the little dots here, right? The gray color dots. So the dots are overlapped. So they are both N-wells. So in the foundry, when they are doing the deposition, they will know that these two N-well areas are overlapped. So if you cut it through in the middle here, for example, and it looks from the cross section, it looks like this because they both, this N plus material here and this PMOS, they are being put in the same N-well. Why? Because the dotted area are overlapped. That's very important when we are doing the layout. Because if you grab a little N-well tap, it has its own N-well, the dotted area has its own N-well. And the PMOS also has its own N-well, which is a dotted area. So you have to make sure that they are overlapped. So when you are doing the layout, right, you grab an tab, grab a PMOS, you have to move them close enough so the dot area get overlapped. So from the cross-sectional view, you see that both N-tab and the PMOS are in the same N-well. However, if you look from the top, what's going to happen? If you look from the top, for this whole, the same thing, okay, from the top, it has N-well here and has a bigger N-well here for the PMOS. There are two different N-wells from the top view because you are laying out the top view. But if you cut it in the middle from the cross-sectional view, they are in the same N-well. Does that make sense? The dotted area is the N-well. Okay, and now let's look at the SPICE code real quick. It's over here. What are the signals being shorted to ground? Because we are sweeping VD, so VD is definitely not permanently shorted to ground because of that reason. Because we are sweeping it, it's a variable, will be changed over time, voltage, because VD x-axis is voltage. But however, all the other places are shorted to ground. VW is also shorted to ground. Does that make sense? I mean, VW, the body here, which is a tab, you'll see sometimes it drew a line in the middle of the symbol, and that represents the body of the well, which is over here. Too much information? I'll let you guys take a look at this for a little bit. I'm gonna grab a napkin real quick. Take a look at this, right? So if there's a line in the middle, you see here, like this. In LT SPICE, it's gonna line in the middle, but in electric, if you bring a 4-terminal device like this, it's a 1, 2, 3, 4, right? It's 4 terminals. Then the one in the middle will be a body contact. It's the body of this transistor, which is this guy. So did you see there are 4 terminals? Body contact, source, drain, gate. Okay? And for the CMOS technology, since it's so old and so simple, there isn't any differences between source and drain. They are symmetrical. Same node, same material. But in some advanced node technologies, they may have a thicker drain in order to handle higher voltage. So there's a certain technology called C5 high. C5 HV, I'm sorry. C5 HV is high voltage C5 version. So that one has a thicker drain, so I have to use that terminal as a drain. But for this very simple technology, source and drain are symmetrical. They are the same node. You can tell that from the layout here. Did you see any difference? Keep in mind, this is the mask. So this is a physical design eventually being put onto the wafer. And you don't see any differences between source and drain. Same material, same masks. Make sense? So they are the same nodes, but you just use one of them. You label them as the drain and source. It doesn't matter depending on how you connect the voltages. So we'll see how these transistors are getting operated later. So you can see these voltages. Source is shorted to ground. Okay. Because we can tell source is shorted to ground, and well is also shorted to ground. So in here it's like ground, ground. What else? G is also shorted to ground. How could that work? What else? D is shorted ground, but the thing is you are doing a DC sweep, so it doesn't really matter because eventually D will be swept from 0 to 5. Am I seeing a different transistor now? Oh, it's a different transistor, I'm sorry. It becomes NMOS. I'm trying to look at the PMOS. That's why it looks weird. Hey, we're looking at this one. Okay, so source ground, W ground, G ground, and VD is getting swept, which is from 0 to -5 volts. So this guy from 0 to -5 volts. -5 volts, keep in mind. So remember when we are talking about PMOS, we would like to short the N-tap here to the highest potential of the circuit. Does it still apply to this principle here or no? Is it confusing? Too much information? But it's very important, okay? So look at this. Remember P-N junction, right? So P and N forms a diode. So that's why we want to short the N well to the highest potential of the circuit. But now you're grounded. Why? It's just a simulation. Is ground still the highest potential of the circuit or no? Yes, it is. See? The SPICE code is giving a 0 to -5 volts to drain. So there's nothing higher than ground in the circuit. It still works. All the voltages are relative. As long as I have a potential drop, it's going to directly run all these kind of current curves without any problems. It's fine. But can you change it? I think you can. It just a little bit confusing, but eventually it plotted something like this. All right, let's take a look. If I have both here and here being shorted to ground, okay, then what's going to happen? You told me source and drain has to have a voltage drop which is higher than VTHP. Yeah, this is actually a very good example. In order to turn on the PMOS, but now it's not a case anymore. You grounded both. There's no voltage drop. There's no VSG. But how that works? How could you still get this curve? Think about it. This is a really good example. Did I tell you it's symmetrical? So what if we don't treat this one as source? What about that? From 0 to -5 volts, and the gate is sweeping from 0 to -5 volts. Gate voltage, even though it's grounded over here, but the SPICE code is sweeping this one from 0 to -5 volts. No, it's a step. It's running different steps from it's -1 volt for each step. So it's from 0 to -5 volts, which is each curve is different V gate voltages. So even though it's grounded over here, but eventually this one overrides this initial ground. So eventually the V gate voltage have different voltages from 0, -1, -2, -3, -4, -5. So this one is actually not grounded. It changes from 0 to -5 volts, and with a step of -1 volts. So it's basically -1, -2, -3, -4, and -5 for these 5 curves. 1, 2, 3, 4. 5 is over here. It's overlapping with here, which is I think is -1. It's in the cutoff region. So in that case, this actually works. We don't have to change it back. But it's good to know it's symmetrical. We don't have to change it back. So let's just treat this as source. This is drain. It's gonna work because VG is getting overwritten by this code. Okay? So VG is actually negative. So in that case, VS is grounded, so S2G becomes positive. Okay, you got positive VSG. So you're able to turn on the PMOS without a problem. So eventually there's a voltage drop over here. Okay, because of V gate. The gate voltage is negative. So you do have a VSG. And because here's 0 volts and VD is from 0 to -5 volts, it's sweeping on the x-axis like this. So you are getting a positive VSD drop, even though source is ground. Doesn't matter, it's still higher than D, so you're getting a positive voltage drop from S to D. So you are having positive voltage drop from S to G and positive voltage drop from S to D, so it's gonna operate. It's gonna run current through S to D. Any questions on this by far? I know it's confusing the first time at the very beginning. Could be very confusing. Any questions on this? Remember when we are talking about the operation of the PMOS, it requires a drop from S to G and a drop from S to D to drive the current through the channel. So the drop from S to G will open up the channel, and this one will run current through the channel. So that's the two requirements, right? So in here in the SPICE code, we can tell that for the PMOS in this layout, we do have a positive drop from S to G because gate is negative, and we do have a positive drop from S to D as well because the drain is negative, even though S is 0. Okay, and then if you look at here one more time, the body here is also shorted to ground because of the SPICE code here is VW equals 0, which is also fine because 0 becomes the highest potential in the circuit. So we are not forming any forward biased diodes in between the P plus and N well. We'll repeat this in the future if you don't get it now, which is fine. And in that case, because you can see from here it's from 0 to -5 volts, and that's why LT SPICE draws that voltage sweep. It just prefers that drawing a lower number on the left and higher number on the right. So eventually it sweeps from left to right, but eventually you are seeing a -5 volts to 0 volts on the x-axis. So, for example, if it's 0 volts for the gate, what's going to happen? Just look at this one, 0 volts for the gate. It's closed because there's no drop between S to G. And that is why it's getting here, there's no current. So whenever you are having a lower voltage to the negative side for the gate voltage here, okay, so the voltage drop between these two are getting larger, and that's why the x-axis D. Okay, so I'm talking about VD actually. So when this one getting more negative, you are getting a bigger drop from S to D, right? So eventually it's getting more current and eventually saturates over here. Okay, if you see a curve like this on Thursday, you know what's really happening here. Or maybe you don't know. Do you? We'll repeat this in the future, okay? Don't worry about that. It looks weird, right? It just looks weird. But if you modify the circuit a little bit, I'm pretty sure you can see a curve like this. Okay, it's a more common curve. One more thing here, also very important. So the PMOSes, it turns out that we can use PMOSes, the NMOSes as pass gate. You'll see this a lot in the future. Pass gates. Okay, so it's being used as a switch. If you short this one to ground, so So whatever voltage is over here, you are expecting that it can pass the voltage to the other side. It's being used as a switch. And now let's see what the limits are in order to do this. I already told you S and D are interchangeable, so it doesn't matter which is which. Don't worry about that for now. Is it able to pass the whole thing to the other side? If I ground here, let's see. So if I have a 0 on one side, what's gonna happen? 0 volts. What's gonna happen? You got 0 volts here, you got 0 volts here, there's no drop. This is G, right? This is G. If this becomes a source, for example, this is a source, it doesn't matter. It could be here as well. It doesn't matter. So 0 volts cannot pass this PMOS to the other side because there's no drop. So this transistor is off. Does that make sense? Okay, whenever this starts rising, like a pulse starts rising, whenever it reaches what? VTHP, what's going to happen? So the voltage here, okay, the voltage here reaches VTHP, and the voltage here to here becomes VTHP. So the S to G drop becomes VTHP because this is grounded. It's grounded. So whenever this terminal's voltage is equals VTHP, you are getting a VSG, which is VTHP, and it turns it on, and that VTHP starts reaching to this terminal. Okay, it's not going to do anything here, but it's going to reach the terminal starting from here and until it reaches 5 volts without any problems. Whenever this reaches 5 volts, or the highest voltage in the circuit, anything can pass to the other side. It's because it's any voltage above this line will be higher than VTHP. Okay, it's giving you a VSG higher than VTHP. What's that?
Does it lose VTHP in the voltage? Like, does it drop?
Yeah, so that's why this part is not passing to the other side. It's losing. So PMOS is not good at passing what? Zeros. We're talking about digital circuits, right? Which means we only care about 0 and 1s. So in that case, PMOS is not good at passing zeros. We don't worry about all these intermediate volt values. We just want to know like zeros can pass through the PMOS or not, but eventually it cannot pass the PMOS. But the 1 can definitely pass the PMOS. Okay, so this is one type of pass gate, or PG. So keep in mind, PMOS is good at passing what? 1s. PMOS is good at passing 1s, but not good at passing zeros. Because of that, all right? Let's look at NMOS. We usually connect here to VDD, which is 5 volts in our circuits, okay, to 1. And so whenever you have a voltage oscillation here, you want to pass it to the other side, but actually you won't pass everything. But now let's see, what is this guy good at passing? So whenever it's 0 volts, okay, since it's symmetrical, and you can tell that if this on the left hand side from the VGS, okay, this is a gate, right? This from the VGS, then 5 to S voltage difference will be 5 volts. So definitely 0 can pass, no problem. Okay, keeps rising until when it stops passing through the gate. So it's able to pass until point. Like 0 volts. Can 1 volt, can 1 volt pass through the NMOS or no? Yes. 5 to 1 difference, it forms a VGS. The difference is like 4 volts. The threshold voltage of the NMOS is like 0.8 volts. So no problem at all. 2 volts, of course. Until when? 4.2 volts. Why? Because whenever this guy reaches 4.2, the VGS here becomes what? 0.8. Okay? If it keeps rising, it's going to keep shrinking that difference. So whenever it's smaller than 0.8, this one's shut off. Okay, nothing can pass anymore. So eventually what? Eventually it can pass until 4.2 volts. Okay, but you know, it's a digital circuit. We don't care about like 4.2, 4.1, 3.5. We don't care. We only care about 0 volts. 0 volts is able to pass through the NMOS, which is good, right? So we now have the NMOS is good at passing zeros. Okay? And that is why. So in that case, if we want to pass both types of signals, there's a new gate called transmission gate. Or TG instead of PG. PG is the pass gate. Pass gate is a one transistor gate trying to pass a signal. And transmission gate is called TG. It's like this. Has the NMOS and the PMOS. On the top is the PMOS, on the bottom is the NMOS. Okay, and you want to short this one to ground, and you want to connect this one to VDD at the same time. In that case, this is able to pass both and ones, 1 and zeros, without any issues. Okay, and that is why our technology is called CMOS. It's complementary. MOS, metal oxide semiconductor, so CMOS, because we need both PMOS and NMOS to pass 1 and zeros at the same time. Right? Digital circuits are oscillating between 0 and 1s, right? So we need both transistors to operate in the circuit. Okay. And there's a different type of connection called diode connection of the transistors. Diode connection of the PMOS and NMOS. So the way that works is you have a PMOS like this, source drain gate, and you short it. You short these two terminals, and for the NMOS, here's drain source gate, and you short these two terminals. And in that case, both transistors are operating in the saturation region. And why that? Let's look at NMOS first. So remember the VDS to IDS curve. Okay, here's VDS set, which is VGS minus VTHN. Okay, and this region is saturation. And for the digital circuits, we always operate the circuits, transistors in the saturation region here. And the requirements is the VDS has to be larger than VDS set, and that's why how we name it. It's a VDS set. It's a minimum voltage to get into the saturation region for the transistor. So VDS has to be larger than VDS set, keep in mind, in order to operate your transistor in the saturation region. And VDS set equals this guy. Equals this value, okay? And if we short the gate to the drain, okay, so VDS equals what? Do you agree with that? No problem here, right? So it definitely is larger than something minus another positive value here. So because VDS equals this one, so VDS must be larger than this. So VDS somewhere here. Make sense? This equals this, larger than this. So which means VDS is larger than what? VDS set. Okay? So what does that mean? It means if you short the gate to the drain, you can definitely operate this one in the saturation region, for sure. As long as VDS is not too small, right? You just have to give a decent voltage across these two terminals. So in that case, we call this connection type of connection is diode connection. And the same for the PMOS. You just short it from the gate to the drain. The same thing. It's going to be operating in the saturation region for that guy as well. Okay. And there's an equation whenever you operate the transistors in the saturation region. There's an equation dominates the current from the drain to source. Let's just take the NMOS as example over here. IDS equals KPN, which is a parameter from the textbook. It's a constant from the foundry, okay? And this is called the square law equation. So Kpn is a constant, and that's the width and length of the transistor. So you can see if you have a pretty wide, very wide transistor, you are getting more current. So a wider transistor is a stronger transistor because it pulls more current. Whenever it pulls more current, it drives whatever the following circuit more efficiently, because all these all these digital circuits, they have parasitic capacitors. So I have all these parasitics, all these little caps and resistors. So digital circuits, remember the time delay we learned at the very beginning of the semester, right? So it's always charging and discharging the digital circuits. If you have more current, it's very similar to like a pipe putting current into a bucket. Okay, you have a more current, you can charge and discharge the bucket quickly. Okay, it's like you filling it up quickly, and also you are pumping out water very quickly as well if you have more current flowing in the pipe. So in that case, higher current means a bigger or stronger driving capability. The driving, so it's able to drive a larger scale of circuit with a lot of parasitic capacitors and resistors in there. Okay, so bigger current, larger current represents a stronger driving capability. So it's able to drive a larger scale of circuits. So in that case, because this is a foundry constant, you are not able to change it. So the only way you can change the current is by increasing the ratio from the width to length. But usually we don't change the length too much. We don't change the length because we just want to use the minimum length always. Okay, the minimum length defines the foundry's technology. Remember I told you guys, if it's a 20 nanometer technology, then the minimum length will be 20 nanometers. If it's a 500 nanometer technology, the minimum length in theory will be 500 nanometers. But however, for our layouts, we don't want to just use all the minimum ones. It's going to decrease the yield. Okay, so probably you're getting a lot of failing transistors in the circuit. So we use a 2 lambda rule, and it's 2 times 300 nanometers because 1 lambda is 300 nanometers. So eventually you're getting 600 nanometers, which is slightly larger than 500 nanometers. That's the foundry's technology, which is 500 nanometer technology, the minimum length they can fabricate in the chip. But we don't want to directly use it. We use 2 lambdas, which is 600 nanometers, so it's a little bit larger than this. Eventually, the minimum length for every single transistor in the circuit will be 600 nanometers. That's a minimum length. So if you have a minimum length, so the length is usually, especially for digital circuits, we don't care about the gains and everything. So in digital circuits, we always use the minimum length in order to do what? Reduce the footprint of the circuit. We have a limited area in the chip. It's super expensive. So we want to limit the footprint of the circuit on the chip. So in that case, we just have a certain, we just use the minimum length of all the transistors, and we just adjust our width because the current depends on the ratio. If you have like two times the length, you have 2 times 2 for the width as well in order to reach the same current. Right, so it doesn't make sense. We just use the minimum length to reduce the area, and we just adjust the width of the transistors to adjust the driving capability of the transistors. If you have bigger circuits, bigger parasitic capacitors, we just use a bigger width to give more current to the circuit. Any questions on this? Now let's look at one example, the calculation. So from the model, from the textbook, KPN equals 120 microamps per V square. That's a constant. And if this circuit is given to you, no, it's NMOS. Two volts here on the top as a VDD, 100K, and it's a gate drain shorted diode connection. And the ratio is 10 to 1, okay? Doesn't have a unit, it's just 10 to 1. And it's asking you to calculate the current, which is IDS here. Okay, because this voltage here is not given, right? It's the same node as here and here. So first equation is IDS, is a square law equation, equals, since we don't know if this guy is being operated in the saturation region, we just assume this is operated in the saturation region, so the equation looks like this. KPN, which is a constant, width over length, which is 10 to 1, VGS minus VTHN square. This is the first equation we have. And the second equation, 2 volts minus VGS over 100K is also IDS. See, this the node voltage at this point, which is VG or VD. But the thing is, S is ground, so VGS is basically VG, and VG is VD. So it's going to be the voltage as this node. So VGS is the same as VD. Because S is 0 volts. So VGS is the voltage from G to S. S is 0 volts, that's why VGS equals VG. And because it's shorted to here, so VG equals VD. And that is why 2 volts minus VGS is basically 2 volts minus VD. It's going to be the voltage across this 100K resistor. Okay, divided by the resistance, you are getting IDS as well. It's just one channel. The gate is not getting any current into it because the gate is a dielectric material. There's no current. See, no current, no DC current. Okay, so there's just one current from top to bottom, and it combines these equations. And eventually it calculates VG. It's not an analog class, so we're not going to get into the details for the calculation. So VGS equals, you're getting 2 answers, 0.933 volts and 0.65 volts, interestingly. You're getting 2 answers for VGS. The reason for that is you assumed that it's being operated in the saturation region, but eventually you're getting 2 answers. And the thing is, only one works, so I have to pick up one. I have to pick up this one. This doesn't work because this is larger than 0.8 volts, which is VTH. N. So this is the real answer. This is the fake one. So eventually I pick up this one, and which makes things possible. So VGS eventually equals 0.933 volts, and you plug into here, you can calculate IDS. Okay, so it's just a practice on square law equation. Do you have any questions on this? So any day without a quiz just becomes so boring, right? All right, let's call it. See you tomorrow.